Good evening, everyone. Okay, last class in AMC 10, 12 seminar, I had left at this question that the sum of first 2011 terms of a geometric sequence is 200. Sum of the first 4022, which is like the next 2011 and the first 2011 included, is 380. Of Then you are asked, K, the three times that sequence length, what is their entire sum? So it turns out it is 542. The reason is simple. Here I have written down the first 2011 numbers ka sum of the geometric sequence. And if you want to go up till 4022, the expression becomes like this. This is the expression for a finite sequence of sum of finite sequence of geometric progression. This is also the same format may written. And you have 6033 like this. So what you should actually do over here is that take a difference between these two. 180 becomes, let's call this equation 1, equation 2. If you do 2 minus 1, you get 180 equal to a times r to the power 4022 minus r to the power 2011 upon r minus 1, which becomes r to the power 2011 times a times r to the power 2011 minus 1 upon r minus 1. What I've done basically by taking a difference between this term and this term is that I have found that it's a multiple of r times, I mean, a power of r times the original quantity. So from here, I can write that this is r to the power 2011 times 200, because this quantity is 200 from the first line of the question. Sum of first 2011 terms is 200. That I will replace with 200. And this gives me an idea for r to the power 2011, that is equal to 180 upon 200, which if you calculate is about 90%, yeah, 9 upon 10. Then what I can do is I can call this x. I don't know what it is, correct? So the difference between equation 3 and 2 will also reveal something interesting. X minus 380, 3 minus 2 will give you x minus 380, and that will be a times r to the power 6033 minus r to the power 4022 upon r minus 1, and that is a r to the power 2011 the whole square times r to the power 2011 minus 1 upon r minus 1, and this put together is 200. This we already know is 90% or 9 by 10. So this becomes 200 times 9 by 10 the whole square, which gives you 162, because 81 times 2. So x automatically becomes 380 plus 162, which is 1, which is equal to 542. Okay, that is the entire solution for this question. Anyone remember this question? It was 2 weeks ago. A lot of stuff happened between 2 weeks ago and today. How many of you were in last class? You can just raise your hand or something. If everyone is new, then there is no point of discussing this. Okay, no problem. Okay, as usual, I will update the share link, and I'll put the share link in the chat so that it's available to all of you. Okay. I have sent a link in the chat. You can access the notes, lecture notes for the past few classes from there. Sanya is asking कि this formula works if r is greater than 1. The thing about this formula is that when r is greater than 1, numerator denominator are both positive. If r is less than 1, even then it will work. Obviously over here r is less than 1. Okay, if r is less than 1, see the general formula I had mentioned over here. I don't want to write it again. Huh. Sum of n terms of a GP. You can use this, or you can even say that a 1 minus r to the power n upon 1 minus r. It's the same thing. Numerator and denominator both you are multiplying by minus 1 and rearranging the terms, which is the same thing. Okay. Nutan is asking AMC 8 link. AMC 8 link I'll provide next week when I'm doing AMC 8. I'll have to open up the note. I don't know where it is at the moment. Okay. Do I put a lecture number anywhere? Okay, just lecture name. So today we'll be doing some number theory, mainly to do with divisibility and fundamental theorem of arithmetic. Okay, one time taking but fruitful exercise in my opinion. List all the prime numbers from 1 to 100. If you have already done this ever in your life, then do from 101 to 150. Okay, I'll give you 5 minutes. Let's see how fast all of you can do it. This is AMC 10, 12 seminar, which is fine if AMC 8 students also attend it. The idea I want to show is you don't need to check all prime factors of a number in order to ascertain it is prime or not. This is AMC 10 12 seminar. AMC 10 12. First, I'm not telling you to find the number that is correct from 1 to 100. What will be the number of primes from 101 to 150? Try to find that also. Try to find as many prime numbers within the next 3 minutes. I will then list out all of them. Okay, I'll let you guys know. From 1 to 100, there are 25 prime numbers, and from 101 to 115, there are 10 prime numbers. So count up if your number adds up to 25 or 10, there is a good chance that you have found all of them. If it does not, then you have missed a field here and there. Okay, I'll start writing down the smaller ones. 2, 3, 5, 7, 11, 13, 17, 19, 23, 20. These are the prime numbers from 1 to 100. Okay. And next 50 prime numbers. This will be slightly tougher because you're not actually used to looking at numbers from 101 to 150. Just a second. Okay, I'm not. There is still a lot of confusion regarding whether this is AMC 10 or AMC 8 seminar. Uh, it is supposed to be AMC 10 seminar only. Seminar number 12, AMC 10-12 problem solving seminar. Okay. From 101 to 150, the prime numbers will be 101, 103, 107, 109, 113, 127. Okay, some interesting stuff to explore is you are able to see there are rows that are forming over here. Correct. Each row is corresponding to every 10 numbers. Now, now this is an open question. You can go and start exploring whether there is a row that is completely devoid of prime numbers. Is there where is the another next row that is completely full of those four prime numbers? Because every number between every 10 numbers, you can maximum have only four, or I mean from like x with 0 to x plus 1 times 0. Uh, there will be only four prime numbers because there are five odd numbers and one of the odd numbers will be divisible by 5. So try to think where will be the next row that is full of prime numbers. This is one more. Okay. Now coming to like actual questions from AMC. Try to figure this out. How many divisors of 12 factorial are perfect squares? So when I say 12 factorial, I don't mean the number 12. I mean 12 times 11 times 10 times 9 dot 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 all the way to 2 times 1. Now you need to figure out how many divisors of this expression are perfect squares. I hope some or all of you know how to find the number of divisors. I think that is known to everyone. If you have a number like a number capital N is equal to P to the power uh, some A, Q to the power B, R to the power C, and so on, where P, Q, R are prime numbers, distinct prime numbers, comma P, comma Q, comma R are distinct primes. Then number of factors of capital N will be uh, A plus 1, B plus 1, C plus 1, and so on. So, keeping this in mind, try to figure out what will be the number of perfect square divisors of 12 factorial. Ayush, not correct. I think you have missed something. I can't exactly point out what you might have missed, but something you have missed. So Mehak is asking what does distinct prime means? Distinct means different. Primes are prime numbers. So all of P, Q, R, and so on are all different prime numbers. There are no two uh, variables over here or placeholders that are the same prime number, and all are prime numbers. Okay. Jilesh, correct answer. Very good. If you have any doubts, you can unmute and ask also. Ayush, correct. Ayush, what mistake had you done before? Uh, are you not correct? Try again. Okay. So first of all, I will figure out what is the expression of 12 factorial in terms of this P, Q, R, and so on. That is the first thing I should do. So uh, what I will mention now is 12 factorial can be written as 2 to the power something, 3 to the power something, 5 to the power something, 7 to the power something, and 11 to the power something. There will be no other prime numbers that come up because 12 factorial maximum goes up to the number 12, and uh, any prime number that is larger than 12 will not divide it because none of these numbers are divisible by any prime number larger than that number. Correct. In Angel Asti, correct answer. Pushkal, not correct. Shivam, not correct. Abhyuday, not correct. Ayush, not correct. Acha, incorrect power of 2. Acha, fine, fine. No problem. So, 2, 3, 5, 7, and 11. How to figure that out? You have 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. So first of all, I can just count up the number of powers of 2. There is a formula to do it, but for such a small example, I can just count it up. 12 gives me 2, so I'll keep a mental count of how many numbers I have. I can also make tally marks for powers of 2. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So I will instead put 2 to the power 10 over here. 3 is how many powers do I have? 1, 2, 3, 4, 5. So I'll write 5 over here. And 5 appears only twice. So this I can do with green. 5 appears once over here, 5 appears once over here. So it appears only twice. 7 and 11 each appear only once in this entire sequence. There is 7 and then there is 11. So, and we know okay, no other prime numbers are going to come. So this is the prime factor decomposition of my number 12 factorial. So if someone had asked us what are the number of factors of 12 factorial, just do 10 plus 1, 5 plus 1, 2 plus 1, 1 plus 1 and 1 plus 1 and multiply it out. That will be number of divisors of 12 factorial, which is not asked in the question. You want to find the number of perfect square divisors. So now what are perfect squares? Perfect squares are of the form uh, if capital N is equal to perfect square and it is equal to p to the power a, q to the power b, r to the power c and so on, then my claim is that each of a comma b comma c must be even. Because if you want to take a square root, if you take square root of this number, that square root will become 1 by 2, 1 by 2 on each of these powers. And if it's a perfect square, its square root will be an integer. So to have an integer, you will have the powers ka half to become an integer. So we require each of a, b, c to be an integer. So now what I'll do cleverly is write 12 factorial as 2 square to the power 5 times 3. Keep this expression in mind. From here only I'm writing it down. 3 to the power 3 square, the whole square, times 5 square power 1 times 3 times 7 times 11. This entire expression has been split into the perfect square parts and whatever remains left over. Now, only this part will actually help us figure out the number of perfect square divisors of 12 factorial. Any of the divisors of this when multiplied by 3, 11 and the perfect square divisors of these part numbers when divided by 3, 7 and 11 will not give us any perfect squares because they will be adding up odd number of times and not give us perfect squares. What was the point of grouping them into perfect square units? Because prime numbers is an indivisible unit. We want a number of perfect square divisors. So let us make for our convenience units that we don't want to divide actually. So units like 4, 9 and 25. These are for all intents and purposes for this question equivalent to be a prime number. So if I write 4 to the power 5, 9 to the power 2, 25 to the power 1 times like other stuff that we don't want. This is what the actually I can multiply it out. 2, 3, 1. Okay, 2, 3, 1 we can keep outside. 12 factorial. Now, if you see, we never want to split 4 up. We don't want to split 9 up. We don't want to split 25 up. If a number is divisible by 5, we want it to be divisible by 25 also. So we'll keep it as a unit. If a number is divisible by 3, we can either have it divisible by 9 or 81 and nothing in between. So 9 can come only either twice, once or no times. That is the entire point of this formula. This for if you have powers a, b, c, you can either have this prime number p come once, twice, thrice, all the way up to a times or 0 times also. That's why you have a plus 1 choices, b plus 1 choices, c plus 1 choices, and you multiply them out and you get the number of factors. Same we'll do over here. We'll do 5 plus 1, 2 plus 1, and 1 plus 1. And here, of course, we will treat it as though this number is not a prime number. We don't really want its influence on our number. So we get 6 times 3 times 2, which gives us 36. Okay, I hope everyone understood this. The main thing is to establish the prime factor decomposition of 12. From there, convert it into a usable uh, decomposition and keep only perfect square units. Their power plus 1 plus 1 plus 1 will give us the total number of factors. Okay, Ayub, you can unmute and ask your question. I didn't understand. Okay. So let's do question.
After A, B, C,
Yeah.
when you scroll up, what's the word
Yeah.
you wrote after B? Down, a little bit
Oh,
down.
this is R.
Yeah, no, when you scroll down, yeah, then each of A, B, C must be
Even.
even. Okay, thank you.
Okay. So question 3, try this out. So how many positive even multiples of 3 less than 2024 are perfect squares? This is not as much a counting problem as much it is like reducing the problem down to a very simple uh, problem, and then it comes solved. The condition is that you want to find even divisible by multiples of 3 that are perfect squares and also less than 2020. Okay, everyone keep working on this. So Angel is asking, why am I doing a plus one over here? So while building up factors of my number, let's say any number capital N, which can be expressed in this manner. If I simply talk about normal factors, not perfect square factors, then in each of those factors, I can ask a question to each of these prime numbers. Prime number P, prime number Q, and prime number R. I can go and ask prime number, how many times do you want to come in the factor? It could be either 0 times, which makes it p to the power 0. So if I write a factor of n, f is equal to p to the power something, q to the power something, r to the power something. This I can ask p whether it wants to come 0 times, 1 times, or maximum a times in that factor. That gives us a plus 1 possibilities for p. Similarly, b plus 1 possibilities for q, and r plus 1 possibilities for r. Sorry, c plus 1 possibilities for r. So that is why you multiply it out that way. And here our indivisible unit 4, 9, and 25 each appear 5, 2, and 1 times. So for them it is 5 plus 1, 2 plus 1, and 1 plus 1. Ha, Ayush, correct answer. Jilesh, correct. Preetham, correct. Acha, does anyone want me to wait? If you want me to wait, I will wait for 1, 2 more minutes. You can just put wait in the chat. Otherwise, I'll start with discussing this problem. Okay, I'll start with the solution. How many positive even multiples of 3 less than 2024 are perfect squares? So let such a number be n. Shivam not correct. Abhyuday not correct. Let such a number be n. This implies 2 divides n and 3 divides n, which implies uh, if n is a perfect square, n is equal to k square I can write. And wherever I have uh, n, I can replace it with a k square. And then each of these implies some very important stuff. Whenever a prime number divides a perfect square, it does not divide it once, it will divide it twice. How you get that idea? Because if 2 divides k square, 2 must divide one of the products, k into k hai. So you can say that 2 divides one of those k's. It can't necessarily be dividing both of them partially, because 2 is a prime number, which gives us that 2 square divides k square, because each of those k's is a even number. And we have 3 divides k, which means that 3 square divides k square. And if anyone is confused by this symbol, if I write a divides b, this implies that b is equal to ak. K belongs to the set of integers. Now I'm writing highly mathematical language for it to be short. In case you find it confusing, you can of course unmute, or you can uh, put it in the chat. You are not finding it easy. Alright. So from here we can say that k square is some uh, product of 2 square and 3 square times something else. So it is 6 square times some m square, because the remaining stuff should also be a perfect square only. In fact, this entire line is not necessary. I could just write this implies k is equal to some 6 times m, because k is an integer. Now this implies k square equal to 36 m square less than 2024. So m square is less than 2024 upon 36. And this is not an exact integer that you need to figure out. 2024 divided by 36, if you do it, you will find it is 1012, 18, 506, 9, and once you divide it again, you get 55 approximately. So m square less than 55, so m less than 7, because root of 55 is smaller than greater than 49 and less than equal to 7. So m has values 1 comma 2 comma 3 all the way up to 7. So total 7 such numbers exist. Okay, try question 4. You can always take screenshot in case you're not able to fast enough write it down. Although I would suggest write it down. Okay, how many factors of 2001 to the power 9 are perfect cubes or perfect squares or both? So it is everything is allowed. Okay, either it's a perfect cube or it's a perfect square or it's a both. Just make sure that you're not double counting. Like you're considering a number as a perfect cube also, as a perfect square also, and also as a perfect sixth power, and you are like counting the same number again and again. Instead of doing that, just find how many factors of this number are either perfect cubes or perfect squares or both. Shivam, not correct. There are many more. Ayush, correct answer. Very good. Acha, realize that 2001 is not a, sorry, 201 is not a prime number. It's divisible by 3 and 30 and 67. correct. Abhyuday, what you have found is perfect squares, I think. Not perfect square, cube, everything combined. Angel, correct. Am I pronouncing the name correctly? Or is it Angel? Or Dilesh, correct. Pushkal, I didn't understand. That is too much, that is much larger than what is possible. See, I'll start partially solving the question. 201 to the power 9 can be written as 67 to the power 9 times 3 to the power 9. Correct. And this is the acceptable prime factor decomposition of this particular large number. This is also going to be very large. The thing you have to identify is that you can figure out the number of perfect squares by writing this as 67 square the whole power 4 times 3 square the whole power 4 plus 67 times 3. It's not plus, sorry, multiplied by 67 times 3. Now this is an indivisible unit that will help you make perfect squares. You can also write this as 67 cube the whole cube times 3 cube the whole cube. Now, whenever a number will be divisible by 67, perfect cube will be divisible by 67. It will be either divisible by 67 cube also, it will be divisible by 67 to the power 6 also, or 67 to the power 9 also. It will never be intermediate anywhere, because then taking a cube root will not give us integers. Correct. So from this and this, you can figure out number of perfect square divisors and perfect cube divisors. Then you have to think what will happen with the perfect sixth power divisors also. Numbers which are both perfect cubes and perfect squares. Shreyas, not correct. Shreyas, I think you have found only perfect squares that are not perfect cubes. Anyone wants me to wait? So here I'll use a concept called inclusion exclusion. I'll include some parts and I'll exclude. This is perfect squares and these are cubes. And these are perfect sixth powers. I mean, the numbers which are squares and cubes will be perfect sixth powers, no? Sixth powers. In total, to find the number of perfect squares, I'll just do 4 plus 1, 4 plus 1 because these are my indivisible units. Uh, they are actually divisible, but for the intents and purposes of this question, they are indivisible. So this will become 4 plus 1 times 4 plus 1, which is equal to 25. And cubes will become 3 plus 1 plus 3 plus 1. So equal to 16. Number of perfect sixth powers, you can also write as 67 to the power 6 to the power 1 times 3 to the power 6 to the power 1 times 67 cube times 3 cube. So from here you can see that only four such numbers are possible. 1, 67 to the power 6, 3 to the power 6, and 67 times 3 the whole to the power 6. So this region of like the common or common part between squares and cubes, or the intersection of both these regions, will be 4. Number of elements will be 4. So total answer will be, first you add 25, then you add 16, and this intersection region has been added twice because it was once part of squares also, once part of cubes also. Remove it once and you will get 41 minus 4 equal to 37. And this is the answer. Okay, any doubts? Try question 5. Here I have a set S, that is set of positive integer divisors of 10 to the power 5 or 100,000. Okay, Pushkal is asking something. Pushkal, 37 is the number of numbers that are perfect cubes or perfect squares or both. Okay, it's not neither. Okay. Question 5 is saying that you have a set S that contains all the prime factors, all the divisors, positive integral divisors of 10 to the power 5. How many integers can be represented as a product of two distinct elements of S? So if let's say P belongs to S, Q belongs to S, and P not equal to Q, then PQ belongs to some other set M. Okay, and this is the only number of elements uh, and this is for all elements M inside M. Better way to write this would be that uh, for all M equal to PQ, M belongs to M, and then this. Okay. So uh, more mathematically I can write that for all M belongs to capital M, and M equal to PQ, this is the mathematical version. Shivam not correct, Anirudh not correct. It will be larger than both your answers. Here I'm not talking about perfect squares. I'm talking about all positive integers. Ayush not correct. Anirudh, You are very close to the answer. Which number did you reject? Only 2 to the power 10 and 5 to the power 10. 2 to the power 10 times 5 to the power 10, that is correct.
Yes, sir.
But there will be other numbers also that can't be represented the same way. Think about what other numbers. And it would still incorrect. There are few more numbers you are missing. So which one did you remove?
One, sir.
One. So there are two more numbers that you have to remove. Amishu, I have already sent it in the group once. I'll send it again. Okay. I'll start solving this question. What you can see over here is that you have 2 to the power 10 to the power 10, sorry, 10 to the power 5. 10 to the power 5 can be written as 2 to the power 5, 5 to the power 5. Correct. And this largest number will be part of P and will be part of S. Correct. And you want two such numbers that multiply to form uh, a particular number that is part of another set M. Jilesh not correct. Shreyas not correct. So what you can basically see is that if you have two numbers, P belongs to S and sorry, P and Q belong to S. If we allow that P equal to Q is allowed, then what is the largest number that you can form that can be part of your new set M? Then M will contain all factors of 10 to the power 10, because the product of 2 to the power 5 times 2 to the power 5 to the power 5 multiplied by itself 2 to the power 5 times 5 to the power 5, that will become 10 to the power 10. And that 10 to the power 10, how many other factors 10 to the power 10 has, that many elements will be in M. But then there are certain situations where to get few factors of 10 to the power 10, you require multiplication by the same number only. Exceptions are when we don't allow P equal to Q, then four cases arise where uh, like those numbers are can't be expressed as product of. I'll give one example. For example, you have 2 to the power 2 square times 5 square. This can be written as 2 times 5 multiplied by 2 times 5. correct? But it also can be written as 2 square times 5 square, correct? This could be a part of S, this could be a part of S, and these two are obviously distinct. So even though 100 can be written as product of two identical terms, it can be written as product of two distinct terms also. So that's where, uh, since it is expressible in this way, this is part of my set n. But the exceptions are, will be 2 to the power 2 to the power 10 times 5 to the power 10, because the only way to get this is the largest numbers ka product. Then 2 to the power 10 only, 5 to the power 10 only, and 1. Now to get each of these elements, you can only express them as 10 to the power 5 times 10 to the power 5. No other factor of 10 to the power 5 can be used to express it that way. This also requires 2 to the power 5 times 2 to the power 5. This requires 5 to the power 5 times 5 to the power 5. And this requires 1 times 1. Again, you can't do this because this is the only way to express this as a factors, a product of factors of 10 to the power 5. So you have 4 cases that will eliminate. Rest all possibilities can be expressed in two distinct elements. So answer will be number of factors of or d of 10 to the power 10 minus 4, which is 11 times 11 minus 4, 117. This function d of something is generally, it's a standard notation in mathematics once you're doing number theory. For other fields of mathematics, I don't know what it might mean. Uh, but in number theory, it is generally accepted that it is counting the number of divisors of a positive integer input. If there is a negative number inside here, then certain definitions change. You might like increase the definition to mean negative factors also. But here we are just considering positive integer factors, and that will be 11 times 11 minus 4, so 2070. 170. Okay, we'll do one more question. Try question 6. Find all solutions ABC such that a plus b plus c is 40 and all of ABC belong to the set of prime numbers. You also have the condition that a is less than equal to b less than equal to c. Ayush, correct. The number of solutions is correct. Anirudh, correct. Very good. I'll give one homework question that you can take with you. Anirudh, Jilesh, correct answer. Okay, here I just want to like demonstrate the idea of whenever you have questions that involve figuring out solutions that are prime only, you can use this good trick of assuming if the number is odd. If you find out that it is not odd, then there is only one possible solution, which is even. Abhyuday, you need to find all solutions. So here it turns out there are two solutions. So assume A, comma B, comma C are all prime. All are, sorry, odd. Okay, this is a good enough assumption because most prime numbers that exist are odd except for two. Uh, so this implies that odd plus odd plus odd equal to 40. But that is just not correct because three odd numbers, if you add them, it is going to be an odd number. It can't be 40. This implies one of A, comma B, comma C must be 2. So this means that if one of these is 2, then if B is 2, then A definitely has to be 2. If C is 2, then both of these have to be 2. So without, definitely we'll have A equal to 2. Correct. This implies A equal to 2. So our question reduces to solving B plus C equal to 38. And now since you have B less than or equal to C, you can just start with possibilities for C where let C equal to 19, 23, 29, 31, 33, and not 33, 37. These are the only possibilities that I see uh, for C being prime number. For these 19 and 31, these give the corresponding values of B. Corresponding values of B is 19 again over here, 17, not 17, sorry, 38 minus, so 15. 38 minus 29 is 9, and 38 minus 30, this is 7, and 37 is 1. So all of these don't give pairs of B and C being prime numbers. So you have only two solutions, 19, 19 and 31, 7. The two solutions are 2, comma 19, comma 19 and 2, comma 7, comma 31. Okay, I'll update the link. You will be able to access the questions and their answers through the link that I put in the chat. Jilesh, answer for 7 is not correct. You can try again. Okay. Think about finding the prime factor decomposition of this number through factorization. And after that, once you have all the prime factors, its decomposition in prime factors, then try to make some pairs and check if you get two-digit numbers only. Okay. That will give you the answer. Use A plus B, A minus B identity, use A cube minus B cube identity, and so on. That will help you factorize this number. Once you get sufficiently small enough units, you will be able to identify if they are prime or not. Okay, that is where you can use this trick. Uh, okay, to check if n is prime or not, you just check divisibility of n with all primes that are less than root n. This reduces the scale of the problem by a lot. For numbers till 100, only 4 numbers need to be checked: 2, 5, 7, and 3. 2, 3, and 5, so instantly you can visually check if a number is divisible or not. 7 is slightly tedious, but most of you might know the divisibility test for 7. 13, 11 are also simple divisibility tests only. Okay, question 7 is homework. Question 6 we did today only. Next class will be 2 weeks later. So 5th say 19th. 19th is NMTC exam also. So if you are attempting it, then all the best for that exam. ठीक है. Next class is on 19th. I'll end the meeting right now. We'll meet after 2 weeks.